All right, well maybe this will make things ever so slightly more interesting because what I figured I got a recommendation to have a look at some of the pseudocode stuff specifically because while it is a small part of the exam, it is in fact still a part of the exam, and I know it's a part that a lot of people's schools will teach really really poorly or flat out not at all. In the case of the message that I got, where someone just flat out was not getting taught any pseudocode from the school. And so what I figured we'd have today, whether or not they show up, it'll be on the recording, would be to grind through a few of the pseudocode stuff. So I'm essentially going to pull up all the past exams, not just from VCAR, but also from other exam providers, because if we just do VCAR, we're going to run out very quickly because it's only been around for 2 years, I think, which would max out at like 4 exams because it tends not to show up in a tech free. You got Tech Active, NHT, the Northern Hemisphere version, for the last 2 years. So we'll get a lot more breadth by looking at the other past exams as well. But okay, cool. So it'll probably be a bit hard for me to continuously drop every single exam that we put into the chat there. So let's see, is that readable enough? It should be. Yeah, these will usually be a one-page thing anyway, with not much context required. So it should be fair enough that they'll go through those questions. Cool. Okay, let's suss it out. So we got an algorithm. Question 17 prints the roots of a cubic. All right, we got that specific cubic that we're printing, or printing the roots of, rather. Okay, the overall goal is to figure out, what is the output of the algorithm? What do we actually get at the end of it? A few things you need to be able to understand is some of the keywords in here. Define f of x works pretty much the same way it works in your CAS. Define f of x, return that, means that f of x is going to get that specific value. So everywhere that you see f of x in the pseudocode, or whether it be f of 0, f of c, that's a really wonky 0. But anyway, any of those, it's obviously going to use f of x as that particular thing. Any of these arrows means that the variable is getting assigned whatever's on the right-hand side. So C is getting assigned the value f of 0. So, I guess in this case, 18 is going to be C. If statements, those are just going to be, you only do what's in the indented spot if that condition is met. So in this case, we know C is 18, C is not less than 0, 18 is not less than 0. So this doesn't happen. We skip over to the end of the end if statement. While loops basically mean that everything that's indented in here will happen forever until this condition is met. Until this condition is no longer met. So this will happen while C is greater than 0. It is currently 18, so it's going to happen. Next statement up. If f of c equals 0, then print c. That we're going to have to figure out. C is currently 18. We don't know what f of c is. So this is where you pull out your CAS. So define f of x equal to that cubic, x power 3 minus 2x squared minus 9x plus 18. Just one quick sanity check to know that yes, f of 0 is in fact 18. At the statement that we're currently at, the if f of c equals 0, that's when we're essentially just going to plug back in here and see what we get. That is in fact not a 0, so the print c statement does not happen. Next up, if f of negative c equals 0, print that. Cool. All right, we'll suss that out. Negative 18. That is not 0, so we do not do the print statement. Final thing that happens is going to be c, the variable, is now going to be replaced with 1 less than what it was previously. So c was 18, now it's going to be 17. End while means we jump back up here. C is still greater than 0 because it's currently 17. Therein lies the loop. So you can imagine what's essentially happening is this is going to loop forever until you hit C equals 0. And in the order that it does things, it will first print the positive version of C and then the negative version of C if any of those work out. This, if you were to do that by hand or by CAS 17 more times, not really that great. So once you understand what's actually happening in the algorithm, it can really help to then use a much more effective method. Can anyone tell me what will be a much more effective method of figuring out what these values are likely to be instead of going through the algorithm end to end?
Solve f of x equal to 0.
Absolutely, yeah. So these are just testing for where the function equals 0. It's testing each individual C value for it. We can just use a CAS solve to achieve that. Many3, 1, f of x equals 0, comma x, and that's going to tell us everything. So we know that the values we've got are -3, 2, and 3. That's cool. We can kind of also see those in the answers A through D. The question that's specific to this is we have to give them in the right order. That's where all that investigation that we did is going to start paying off. Because if you look at the answers we have, -3, 2, and 3, you can't just give them in that order because that won't necessarily pay off. Can anyone tell me what the valid order would be for this?
Is it option C?
Option C. So it's going to be 3, then 2, then -3. What made you conclude C on that one?
Since we're subtracting like 1 from like the actual C, right?
Mm-hmm.
Every time, like the largest value would come first.
Large value does come first. Yep, that's good.
And that's why we should go, like our three numbers, we should arrange them in descending order.
Yeah, in a not descending order fully. The reason why is because these are back to back on each other. It's worth pointing out if this one gets executed, you only jump back off to here, not all the way down. These are in two separate statements, and so because you have a plus minus on here, basically the way it's working is it's testing f of 17, f of -17, 16, -16, 15, -15. Because you've got plus minus 3 in here, it's going to chuck out 3 as the first one, -3 as the next one, and then you're going to get the 2 at the end. So I guess the only thing to clarify there was just because one of these statements ran doesn't mean the other one cannot run either. Fair enough why it's going to end up being D in this case. Sweet. Okay. So yeah, a lot of what you're going to be doing in pseudocode is obviously understanding the actual algorithm itself, but usually you're not going fully end to end on the entire thing, bashing it out on the CAS the entire time. For those who are a bit of a late arriver, we're just basically grinding out pseudocode exam questions rather than going through an exam end to end. Reason why is because even though pseudocode is a small part of the exam, it is a valid part of the exam that's really under-taught. And so what I'm hoping we can do today is make sure that is not a bottleneck. Actually, I shouldn't go to the next one. So usually that appears once in the multis and then somewhere else in the extended response. Let's see if I can find another one in the extended response. I wasn't able to look too much ahead of time for these. Should be easy enough to spot when pseudocode comes up, because you'll see all these nasty words. Yeah, okay, just flat out didn't show up in the extended response. At least not that I saw with a run through on that. So, you know, not overly represented in the exam, but it's still good to be able to get those marks because they tend to be fairly chill. If you look what we did, we just sort of read the code and then did a CAS solve, and then we had to put it in the right order. So it's a free mark where possible. Okay, next one up, another multi. So we've got F, we've got G. We've got a crossover between those two things. the pseudocode below is going to basically help us figure out where these two functions intersect, specifically the x value, actually. Okay. Yeah, we can probably do one more example where I run through it, and then we'll see if we can get some other people to jump in. So again, define statement defines what's going on in the function. The things in the bracket here, we kind of glossed over this last time. They can appear in the actual function itself. Basically, these are the inputs to what's going to be represented in the rest of the pseudocode. So you've got these two values, x0 and x1. You run this statement here, x gets x0. Unless you know what x0 is, you can't really do anything here. That's where this thing sort of pays off here. So which of the following will run, or will the function this return? The order in which these terms are presented is that. And you know, that might seem a bit odd for pseudocode. You actually already do this in the CAS. Whenever you do like a CAS solve or a tangent line, you're always doing stuff separated by commas, and those things are assigned to specific things. Usually it's function comma x or whatever it happens to be. So this works the exact same way that your CAS works. Just want to make that clear enough. So basically this is saying this question here, we have x0 is 0.6 and x1 is 0.8. So when you're going through and trying to figure out what's going on here, you can keep those numbers in mind. So essentially, we know that x is going to get the value 0.6 in this first line of code. Next up, while x is less than x1, is x less than x1? Well, it's currently 0.6. x1 is currently 0.8. Seems appropriate. This next statement here comes up fairly often. Can anyone have a stab at what that's trying to do? Even if you just relate it to things you already know, with like these inequalities perhaps. What kinds of ideas is it bringing up? Where else do we see these double inequalities, where you've got something on the left, something on the right of some set of inequalities? It shows up a fair bit in methods. Where does it show up?
Does it show up in like domains or like probability?
Yeah, domains, probability, integrals, anything where you got some upper and some lower bound, effectively. And that's what this is. This is effectively tolerance. It's if your value of this is between some upper and some lower bound, then great. We'll say we've solved what we wanted to. Now, you might notice cos x and x are essentially the functions f and g. You got cos x, you got x. So when you do cos x minus x, what you're essentially doing is finding the difference of the y values. Right? You're finding out what's the y value of cos, what's the y value of x, subtracting those two things together, and that's going to give you some value, right? Difference between the two of them. This is saying if the difference of y values is between plus minus 0.01, we're happy. We're going to return x, which means the final answer is going to be whatever that x value was that we achieved. And what you're essentially doing there is having a tolerance, which is I'm happy with whatever answer as long as it's accurate to, well, I guess it's going to be accurate to however, what's that, 2 decimal places, I guess? It's probably what that ends up being. I'm not entirely sure that's 100% accurate, but you're basically putting some sort of upper and lower bound on how accurate you want your answer to be. So if that happens, then we return, and that's the entire thing. As soon as you hit return, the entire algorithm ends. Most of the time that's not going to happen, so we're just going to increment x. Specifically, we're going to shift it up by 0.01. So it was currently 0.6, now it's going to be 0.61. We're going to keep doing that until x is no longer less than x1. So essentially, we're going to keep doing that until x hits 0.8 or this happens first. If we hit 0.8, the return statement is going to be no intersection found, which would be answer E if we get there. So from there, we basically understand what's going on in the algorithm. Again, if we were to try and belt out all of these, I think we would do that, 20 separate times if we had to test every single one. What could we do instead that would help out? Or at least make things a lot faster? Think about the overall goal of the algorithm. What we did before was basically use a much more sophisticated CAS program to get the answer ahead of time and then work back from that. Think about what this one's trying to do and how we could solve it in a more CAS-friendly way. If we ignored pseudocode altogether, and I just said figure out where the two functions intersect, how would you do that? Make them equal to each other, correct? Yeah. So we can figure out our answer ahead of time just by doing a quick CAS solve and seeing where those two things are equal to each other. So we'll do menu 3.1, x equals cos x. We'll put a domain on that so we don't get infinite solutions. So we know it's between 0.6 and 0.8. Excuse me, I don't know why I got a bit of phlegm in my throat. Coughing relatively recently, so I'm going to apologize for that ahead of time. So 0.6 to 0.8, we know is roughly where that's going to be. Control Enter, and we can see that the exact value, or I guess the best value we would have would be 0.739-ish. Now, that's not any of the answers in here, which we have close, right? We have 0.73 and 0.74. So that pretty much narrows our focus into what we expect our answer to be. A couple of things to point out. First, is this actually in the domain of things that we expect it to be? Right? This algorithm was going to terminate. It was going to have the no intersection found statement if we got above 0.8. First thing you have to ask yourself is, did this go above 0.8? Obviously not. So we can already rule out E from that. Next up, we have to figure out basically at what point was the difference between these values between negative 0.1 and 0.1 first, when did that first happen? Because as soon as that happens, return X, answer over. We've narrowed it down to two possibilities. How are we going to figure out which of those achieved it? Think about what this if statement's actually saying. These are X values, by the way, returning X. How do we know which of these triggered that first? With the understanding that this is just the difference between the two functions. This is essentially saying when is the difference between the two functions between plus or minus 0.1. first thing I would do is try to figure out what the function is, right? So cos x minus x is the thing we care about. The result of that thing is what we care about. From here, because the answers C and D, we've narrowed that down. Because those are x values, we're essentially going to plug both of those in and then see what one achieves at first. Now remember, in the algorithm, we're adding 0.01 every single time. So we're starting from 0.6 and working our way up to 0.8. So if 0.73 does give us a y value between negative 0.01 and 0.01, then we'll be happy. Rupraj probably has it right, answer D. Let's see if that's what comes out. So we're going to test h of 0.73 and see what actually we get. So, yep, this is in fact out of tolerance. We've got 0.015, not between negative plus minus 0.01 rather. So, I mean, that already tells you it's going to be 0.74, just because that's the only other possible answer. But just for the sake of it, you can see, in fact, yes, that is definitely within tolerance. And so the answer is going to be 0.74. But yeah, as I said before, a lot of it is understand the algorithm, use a CAS to figure out what the actual answer should be, and then use the particularities of that particular algorithm to figure out what will actually be shot out as an answer. Anything to clarify from there? Okay, let's see if this one had an extended response. Yep. Not quite. Still not quite. Yeah, okay. Just really doesn't want to show up in exams all that often. Nice. All right, that was 2024 VCAR. Let's see what Heffernan has to say. It might also show up in exam ones, although it's a bit rarer, so I feel like I'd be spending a lot of time crawling through exams rather than just doing questions. These will be a bit easier to spot if we just sort of grind out the multis, I guess. Yeah, here we go. Okay, algorithm. Should I continue doing what I was doing before, which is explaining the algorithm? Or does someone want to have a read of this and give their best approximation of what's going on? What do you think would be more instructive? Anyone wants to brave it, maybe just a thumbs up or something like that. Happy to let you try and explain it. Cool. All right, I'll continue explaining the algorithms then. Okay, so first up, uses trapezoidal rule or trapezium rule. So already, without even reading any of this, you kind of already know what it does. Trapezium rule, you want to figure out the overall areas of each trapezium and then go from there. So that already frames the context through which we can understand what's going on already. Inputs are defined up here, F, A, B, and N. Those are exactly the same as the trapezium rule, variables. Again, we have this define statement here. Reminder, of course, the order in which those are written matters as for when the algorithm is run. So, function, this is then A, this is B, and this is N. That then allows us to actually plug in some of the numbers. So, first things first, H is going to be B take A divided by N, just like you would do for a regular trapezoidal rule. B take A because you're doing the start and finish of the overall domain, and then divide by N is divide by the number of trapeziums that are used. So that should make enough sense. That'll give you the spacing between each of the trapeziums. In fact, what I should probably do is show what's going on there. I'll just pull out the phone for some notes. There's not my notes tab. Oh no. There we go. That's better. Cool. So what we've essentially achieved there is we've got some function from A to B. I guess in this case it's from 0 to 3. So let's just pretend it's there to there. We were told there is n equals 3 trapeziums. So you'd have bang, bang, 1, 2, and 3. Something like that. And so h being b take a divided by n, it's just what's this distance divided by number of trapeziums. That's going to get you the spacing of each of them. From there, total is going to get the value of f of a plus f of b. That should make a decent amount of sense. F of a, f of b, those are the y values of the trapezium. I know I haven't drawn x squared plus 1. This is probably closer to negative x squared plus 1, but it's, yeah, besides the point, I suppose. So yeah, f of a, f of b. A is, of course, the lower bound. B is, of course, the upper bound. So what you're essentially doing is finding the y values of those endpoints of the trapezoidal rule. From there, x is a plus h. So what that means is if a is your lower bound and h is your spacing, what that's essentially doing is taking you from the left and then incrementing your x value by the spacing every single time. I is going to get the value of 1. You'll find it's pretty common for these while loops to have an exit condition based on some counting variable. Like for in this case, while I is less than n, basically you'll see there'll be this statement here that keeps incrementing I every single time, and only once I is equal to n or greater than will it exit the loop. So that's just there to track how many times we've gone through the loop. I is 1, I less than n. Well, n is currently 3, so let's enter this loop. From there, we had this variable total from earlier. Total is now going to be assigned the value of total plus 2 times f of x. So that should be reminiscent of the actual trapezoidal rule here. So what we've currently done so far is we've got the f of x. Oh, I can't drag these. Hopefully my cursor's showing up. Yeah, kind of. We found the addition of f of x naught and f of xn. All of these things in the middle to f of x. That's what we're basically calculating now with that. So that's what these are doing here. Now, 2 times f of x, you've got to use this x. So since we did x equals a plus h, it was 0. H is, I guess we didn't actually calculate h. It's going to be 1, right? 3 trapezoids between 0 to 3. H is going to be 1. And so we've gone from 0 to 1. We're now saying what's 2 times f of 1 and adding that to the total, overriding it. X gets x plus h. We're kind of ignoring the a now because what we're trying to do is consistently increment on the x variable, not necessarily the a. We just want to keep incrementing by that spacing. I gets I plus 1, and then you jump back up here. So it's currently 2. 2 is still less than 3, so we're happy. Do this again for this next x value. I is going to be 3. Then we exit. So what we've achieved is the 2 outside values from before the loop and the 2 inside values from the 2 times we went through this loop. Finally, area estimate is therefore going to be the addition of all those 2 things multiplied by h over 2. That's going to be the term that was at the very front of the trapezoidal rule, which is that. That's what that's achieving. And so basically, when all is said and done, after having gone through the entire algorithm, this works exactly the same as you would do trapezoidal rule. Which means, having gone through that algorithm, you probably don't actually need to do the algorithm. You can just calculate trapezoidal rule like you're already used to doing on the CAS. So whether you were plugging in X values and calculating these things as you were going through it, as you were understanding it, or if you want to do that at the end, it's really up to you. I tend to be of the opinion that understanding the algorithm and then calculating is a bit faster, because once you understand it, you can, yeah, once you understand it, it makes it a lot more easier to figure out what's actually going on when you're putting these calculations through. But yeah, at the end of the day, you can, now that we know this is just trapezoidal rule, we can do it like we're already used to, which already allows us to rule out some answers. Any answers in here we can definitely rule out.
Can we rule out C and D?
Yeah, C and D. Why is that?
Because the output is just one value, it's just the area.
Yeah, correct. Output's just one value. This print statement is not in a while loop. It should never be able to run more than once, so none of these commas should exist. So really it's just going to be, is my trapezoidal rule the 25 on 2 or 15 on 2? That's pretty much just trapezoidal rule. We're kind of done with the whole algorithm stuff there. I can calculate that stuff if you want for you, if you want to see the ending of that, but it is just trapezoidal rule. Does anyone want to see that, or shall we move on to the next pseudocode thing? Sweet. All right, I'll just have a look at the other multis, see if there's another one in here. I'm going to stop looking through the extended response. I feel like that's just going to waste time. They do, like, take my word for it, they do show up occasionally in extended response. I just apparently had bad luck trying to find it. Let's go with Mav. Seriously, nothing pseudocode? Did I miss it? This isn't really pseudocode, it's Newton's method. Is that what they're doing? Are they essentially saying, hey, here's the new things in the study design, you get one of them? That's ridiculous. Okay, well, if it didn't show up in the multis, then surely it's going to be in the extended. That's insane. Okay, that's fun. Let's go with TSSM. If you spot one and I miss it, like, feel free to call me out, because I am going kind of fast trying to find them. But okay, I did find one here. This is a Newton's method algorithm. How are we feeling? Does anyone want to try and take a stab at trying to explain what's going on in here? Or shall I keep going with them? Because, like, a lot of the skill is trying to understand the algorithm. If you can brave and try to explain it, that'd be probably the most benefit you'll get out of it. Cool, that's fine. I'll keep going. Okay, Newton's method, again, that means we can already have a decent amount of context as to what's going on. 5 iterations, yeah, checks out. We got a for loop from 1 to 5. Inputs, as earlier, so we got f, we got derivative, and we've got the initial estimate. Makes sense. That's how Newton's method works. Define the function. So in this order is the order in which the terms are going to matter. So this is going to be, I still can't drag that. The way they format these things sometimes breaks a bit. Here's your f of x, here's your derivative of f, and then here's your x naught, your initial guess. Cool. So you go straight into the for loop. Now, what you're seeing here is essentially your in fact, did we have a for loop before? Anyway, doesn't matter. For loop from I1 to 5 basically means it defines the variable in the actual loop itself. It's valid, and what it essentially means is you start at the lower bound and increment by 1 up until the upper bound. So every time you go through the loop, you'd have I equals 1, I equals 2, 3, 4, and then finally 5. These should be indented, so TSSM just didn't seem to give a shit. So I guess we'll pretend they're indented. So this is one big indent here. That's where the loop will continue. If derivative equals 0, cause a divide by 0 error. That should make a decent amount of sense based on what we understand of Newton's method. Why is that bad? Like, why is derivative being 0 bad for Newton's method? Okay. Can anyone tell me what Newton's method does, just broadly speaking, the overall algorithm?
Does it find x-intercepts?
Yeah,
Or...
it finds x-intercepts. That's correct. Do you know roughly how it's doing it?
Is it just like through the something to do with the gradient?
Yeah,
I don't quite remember. I think it's tangents until it hits the like x.
Yeah, precisely. That's exactly how it does it. Yeah, you do tangents a bunch of times. So if I draw, I mean, I don't know how good this picture is going to be for it, but let's find out. Let's say we're trying to find the x-intercept, and we know it's roughly here. The way it works is you take a tangent line, and then you use that x-intercept of that tangent line as the next spot from which you take a tangent line. And then you continue doing that, rinse, repeat until, like, you can see already with that little picture, we've already got it like super body close to where the actual x-intercept would be. So with that understanding, why is it that having a derivative of 0 or gradient of 0, why would that be a bad thing for Newton's method?
Means the tangent is a straight line with no x-intercepts.
Yeah, that's it. We take it right here on what looks like a turning point. You got a horizontal line, you don't get your next x value, everything breaks. Return error. You can kind of cheat the system a bit by knowing that's not going to happen because all the possible answers are x values, so you kind of already know you can ignore this, but I guess the purpose of today is to try and explore pseudocode rather than cheat out an answer. But okay. Else, that's just Newton's method, right? Like, they formatted it terribly, but you might recognize that as the Newton's method equation. And so, there's really not much else going on. You're looping this 5 times. That's key. You have to understand you do it 5 times. And the return statement is outside the loop. So basically the final thing you get is going to be what you end up with. Now, point of order there, x0 starts as 5. It gets assigned with a new value. And then once the loop is done, you return. So what's important to understand there is, yes, you're running through this 5 times, so you're updating this 5 times. The x0 that you get as the 5th time is the final thing that you put in there, not the guess that you get on the loop. It's the next guess that you would put back into it. I don't know if that was explained all that well, but let's give it a shot. So this is one where, it's a reasonable amount of iterations to do this. So you would probably just do this entire thing end to end yourself. Define function as x squared minus 8x plus 2. I don't know, let's use b of x. B of x is derivative of h. And then finally, the Newton's method equation is going to be x take h on b. Okay, cool. So I is going to get 1 immediately, and we're going to update x naught with that. So we're going to do c of 5. That's the output after for I equals 1. Then for I equals 2, we're going to get this. For I equals 3, we're going to get this. I equals 4. I equals 5. And then that's sorted. So final answer there is looking to be D, if I'm reading that right. 7417. Yeah, that's looking good. So yeah, you hit I equals 5, and then as soon as I equals 5 is reached, you end the for loop and you return. Fair enough? Anything there left to clarify? Let's see if Neep has anything for us. Sure does. Here we go. Newton's method again. Nice. All right. I'll ask again. Does anyone want to give this one a shot now? This should be quite similar to what we just did, given that it's a Newton's method equation. Anyone want to take a stab? Okay. Inputs, as always, defines what each of these variables mean. Define statement itself, the order in which those variables matter. So when you run this algorithm with a particular input, it's those order that matters. Now in this case, we don't actually have a running of the algorithm per se. We're trying to figure out what one of the missing lines of code is going to be. Okay, approximate square root. Newton's method to approximate the square root of a number. That's interesting. How's that working? Newton's method to do a square root. Yeah, okay, so I guess it's just square root x. Not sure I fully understand that yet. Let's work through the algorithm and see if we can decipher it. If num is less than 0, then error, number can't be negative. I guess that should make sense. We can't have a negative inside the square root. And if these indents are all over the bloody place. X gets x naught, so whatever the initial guess is for the thing is assigned for x. For I is between 1 to n. We saw that before. It's just going to loop up until n, however many iterations you're doing. Does some magic, and then returns what the x is going to be. And so I guess what's happening here is we've got to figure out which of these operations gets us closer to square rooting the number. That's cheeky. Huh. I mean, there's a really brute force way of doing it, which is just doing an example number. So you just like pretend x naught equals whatever. Like let's say number is 10 and x naught is 9. You can just square root your 10, get the number for what that would be, and then run this algorithm with different code in there and see which one gets you to your number. Because if these are too similar, then you won't be able to pick between the differences. So they have to be different enough. That's why you could brute force it. But let's see if we can try to analyze what's going on here. Okay. Newton's method to square root a number. Newton's method finds x-intercepts. So we want to write this in a way where the x-intercept is the square root of a number. So you want the function x equals square root of number. So x equals square root y equals x squared. This one is actually tough. What's going on here? Using Newton's method. So, as we discussed, Newton's method is a way to solve x-intercepts. That's how that function works. So, if we're using Newton's method to find the square root of a number, then whatever x-intercept we end up at should be the square root of that number. So x is the square root of a number. Yeah, this one's weird. We don't have an f of x in here. We just have number and x naught. I don't know if this is Newton's method, to be perfectly honest. I don't see how this is going to apply. We don't have really a function f of x that we're going to be doing. Did they mean bisection? Hang on, did they not? Okay, probably not bisection method. Because these were kind of looking like bisection method. Let's suss it out. So what's actually happening in A, for instance? X plus x by x minus number. Let's write this out in a not shit way so we can actually understand it. X plus x squared, I get. Oh, that's just x by x. X squared minus number on 2x. Okay, that's what that one would have been. What does that get us? I guess that's where that x squared comes from. Yeah, I don't know. This will take me a lot longer to solve, I think. I'd rather not waste everyone's time with me trying to figure out what's going on with this one. If I figure out what's going on, I'll put it as a post in the school. Let's keep these more productive than me just trying to mess around and trying to figure out what's going on. So I'll apologize for that one. Let's see what else we got. Insight. Function, trapezoidal rule. Inputs, the function, the particular things we're going to input into the function. These are all stock standard. It is a trapezoidal rule thing, so we should expect this to look like trapezoidal rule. In fact, this almost looks exactly like what we've seen before. You know, this b take a divided by n, the addition of f of a, f of b, the 2 times f of x, w being the width instead of h. This looks pretty much identical to one of them we've done before, with the exception of it being w instead of h, and they've done... Now that's interesting. They've done it to n minus 1, and the number of trapezoids to use. Yeah, no, that's fair. I think the other one used a while loop, if I remember correctly. That is effectively the same as just saying n minus 1. But okay, so this is going to run the exact same way as the other one. This initial bit is going to find the 2 n values for the y values. Then we're going to loop n minus 1 times. So in this case, it's going to loop 2 times to grab those other other values on the inside. This is, yeah, and there's your W over 2 times the sum. Yeah, this is just the same thing as before. Nothing really to explore there. Unless, I mean, yeah, this is the same algorithm. We've already done this one. What's that? All right, let's pull up 2023, see if there's anything in there. Newton's method, for loop, 3 iterations. There doesn't look to be too much different here. Anyone want to take a stab? It's Newton's method, three iterations. Oh, good. All right, function, derivative of function, estimate. That's those again in that order. Here's the specific functions we're using. There's f of x, there's the derivative, there's the guess. For 1 to 3, we've seen this before. Derivative of value, derivative being 0 is going to give you an error, right? We already explored what was going on there. This, of course, is the Newton's method actual equation. We're looping that 3 times. It even tells us it's 3 iterations. And so we're just going to do exactly the same thing we did before, but this time this is our f, this is our derivative, and we're going to loop that 3 times. You can kind of game it by looking at the answers that are closest to each other. So 1 and 3, not going to work. A, that's just a bit too dissimilar. So you're pretty much just tossing up between B and C. So at worst case, if you still don't get these, you got like a 50-50 split just by gaming the system of multi-choices there. I know at least one of these VCAR exams had one in the extended response. It might be this one. Nah. Northern Hemisphere. A bit too fast there. Did they seriously just not have it? Yeah, I guess not. Surely in the extended response, maybe? Ridiculous. Pseudocode just doesn't show up. Afternoon. Alright, here's the 100th time we've seen Newton's method. Who's going to give this one a shot? Or do you want me to explain the exact same thing 4 more times? I mean, like, I guess the lesson here is you can see the repetitiveness, all right? So you're going to have pseudocode for Newton's method. You could have pseudocode for bisection method. You could have pseudocode for a novel case. We saw one novel scenario, which was just finding an intercept between two spots. But you can see a lot of what ends up happening is they just sort of use the new study design stuff, which is going to be either Newton's method, bisection method, which oddly enough, we haven't actually had a bisection method one yet. Yeah, I mean, that's about it. I feel like these are going to get quite repetitive. So if no one wants to take a stab at it, I don't really have anything specific else to teach. I can keep explaining the same ones over and over again if that's what you like, but I feel like we've tapped out what pseudocode is likely to be. Anything people want me to clarify further or Is there anything else I should do with the remaining 4 minutes or so?
This is kind of off topic, but what is bisection method?
Yeah, I mean, no, that's totally on topic. Bisection method, I can, well, instead of pulling up the textbook, I can kind of show it. Bisection method is where you have some upper and lower bound that you know your x-intercept is between, and you essentially continuously halve the interval. So we're going to have some function like this on the handwritten section. And let's say, okay, I've got this x-intercept here. I don't know what it is, but I know it's somewhere between -5 and 0, let's say. In fact, just to make it easier to demonstrate this, I should probably make that a bit different for an interval. Let's say -5 is here instead. What bisection method does, oh, it's already zoomed in. What bisection method does is it starts by splitting the interval in half. So that would be roughly here. And then testing the y value at that spot. So that would be here. If it's positive, you know that you've still got left to go. If it's negative, you know you've still got right to go. So because this is still a positive number, you then use this as your new domain, and you split that one in half, which would be here. You then test the y value at that spot. You see it's negative. Got to go right instead. So you split the interval in half again, and you test the next spot. Positive, it's got to be between here, and then, eventually you get infinitely close to what's going on there. It's a consistently splitting the domain in half over and over again until you get closer and closer to the thing. And the breakout condition for that is typically a tolerance, like we saw before, which is f is between plus minus 0.01 or something like that. So the y value is going to be between plus minus 0.0 something or other. That's probably the most common breakout condition for it. The other is you could do a number of iterations. So could you say, do 10 iterations and see what you get. If we have a look at like question 14 here, this one was a tolerance on Newton's method, which we can kind of see in the if statement of the PDF. So tolerances, they usually look like the double inequalities, as you probably see there. Yeah, that's bisection method. Make enough sense for that?
Yeah, thank you.
Sweet. Yeah, and that's about it. I'll be here for another 2 minutes, I suppose, if you want me to clarify anything either on topic or not on topic. But yeah, I'm hoping this was at least somewhat instructive for understanding pseudocode. I know I'm hoping it was more just like a bravery thing that no one was jumping in for questions rather than not understanding it. If understanding is still on the tougher side, let me know. I might have to update the course stuff that I have in the school. I do have a guide on typical pseudocode stuff and how to provide and how to approach it. So let me know if this has been non-instructive, and I'll fix it up. Otherwise, yeah, happy to field any questions. Otherwise, enjoy the rest of your day.
Thank you. Have a good night.
You too. Bye.
See ya.